All right, on to week 5. We're talking about intertheoretic relations. There's actually two types of intertheoretic relations that we'll talk about. One is theory change, which we've um, referred to a great deal when talking about scientific realism, right? Because we had to grapple with the fact that we exchange old theories for new theories, and we tend to think the old theories are worse than the new theories. Um, and then the other kind of intertheoretic relation we'll talk about is reduction, but that will be a couple lectures from now. So today we're going to talk about Kuhn and his account of scientific revolutions. It's pretty fun, I think. It's a different approach, right? So we've been involved in a lot of sort of like heavily sort of logic-based stuff and talking about, well, what are the right, is science a deductive enterprise or is it inductive? And what kinds of inductive arguments are we talking about? Are we talking about inference to the best explanation or something else? And so it's been very heavily in logic. And Kuhn takes a more historical approach, looks at the history of science and sort of draws some conclusions from sort of observing the way that science has operated through history. So it might be a refreshing change of pace. So he does this sort of historical analysis, and he actually ends up with some very different conclusions than some of the people that we've seen that are more concerned with logical analysis, like, for example, logical empiricists. So Kuhn, in his sort of, and I didn't assign Kuhn's book. It was hard to find just a particular, a short enough passage that would be helpful. So you're reading the chapter, Staley's chapter from the textbook, that sort of summarizes Kuhn's approach. But he uses in his book a lot of sort of concrete examples from science and examples of how sort of theories change. And it's well written and it's a fun read if you have the time. But we won't be able to get so much into the details. But what he does, the conclusion he draws from sort of observing um, scientific theory change in various scientific disciplines is that there's sort of two ways of doing science. Um, most of the time, most scientists are doing what he calls normal science. And that is, you're sort of relying on the past achievements of sometimes it's a sort of like an Einstein or a Newton or some kind of genius that has sort of like laid down the basic conceptual groundwork, and you are plugging along, sort of using their basic equations and their basic worldview in order to solve some problems that haven't quite been ironed out, right? And that's um, certainly a perfectly good, right, an admirable career for a scientist to have, is to just sort of clear up one bit of a corner of, Einstein's theory, or something like that. And that's the most that any of us could hope to do, and it's a good life. Um, so most of you, if you go on the sciences, will probably find yourselves doing normal science, right? So this framework of normal science that they work within, where they all sort of share the same assumptions, be it Newtonian mechanics or right relativistic mechanics. Kuhn calls this a paradigm, right? So this is um, just a general set of assumptions and a framework within which you're going to work, um, and you're not really going to question some of the most basic aspects of that framework. And we'll see some more concrete examples of what that could possibly mean or what sort of assumptions we're talking about. We will work through one concrete example at least. So within normal science, certainly there will be disagreements, right? And people will be competitive, but there's going to be very little disagreement about the fundamental conception of the discipline that they're working in. But eventually, Kuhn notices, right, as he looks through history at the history of theories changing, um, there's little problems. People are working away at solving them, right, in normal science, and they're solving a lot of them. And then maybe one seems to it's real pesky. Nobody can seem to quite sort it out. Well, that's not a big deal, right? We'll keep working on it. But as more and more of these pesky little problems crop up, which he calls anomalies, right? Um, Data that can't be explained by the current theory, um, this starts to be a problem, right? More and more anomalies, it starts to become fairly obvious to people that they're not making progress anymore. So here's the example that Staley uses, which is the Bohr model of the hydrogen atom. Once upon a time, I think when I was in junior high, this was basically the account I was taught, right? So you have um, your nucleus, and then you have these orbits, right? And electrons, uh, right? Each orbit can handle a certain number of electrons, and they typically stay within those orbits, right? They don't sort of hang around in the middle part in between the orbits. Occasionally they do jump, leave their orbit, right? And they'll emit a discrete sort of packet of energy when they do that. So when they make these jumps, they're like sort of abrupt, discrete jumps, right? So according to this Bohr model, there's not like a continuum of sort of areas where electrons exist. It's one place or another, and if they move from one to another, it's a very fast, discrete jump. Um, and this explained some stuff, right? There was a reason for positing this. Hydrogen appears to emit light in a very discrete spectrum, right? It's not sort of a continuous spectrum. It's very specific, and this can be explained by the behavior of these electrons in these shells. And this Bohr model of the atom worked quite well for what we call two-body systems, where you've got a nucleus and then a group of electrons that are basically so close together you can kind of treat them as one body, right? Um, and then maybe one electron further out that counts as the second body. So that's fine if you have a nucleus, right, and you have a shell with one or two electrons, and then just one stray electron in a shell that's not completely full. Um, that's fine, right? That the Bohr model worked great for that. It didn't do so great for other configurations, right? If you had sort of two electrons in an outer shell, all of a sudden you weren't getting the predictions weren't working out, right? It didn't predict the Zeeman effect, so if you put an atom in a magnetic field, all of a sudden you get sort of a blurring of these very discrete states, which shouldn't happen, right, under the Bohr account, right? Any movement should be in these discrete jumps. All of a sudden you're getting sort of a kind of a blurry continuum when you introduce a magnetic field. So there's a couple of anomalies, right? As these pile up, you get what Kuhn calls a crisis. So in a crisis, the people engaged in the normal science are starting to think that they can't ever solve anomalies, right? Um, and this is a problem because they can't really work outside of the paradigm, right? And what Kuhn realizes is that the problem probably is the paradigm itself, right? The reason they can't solve these problems is they have these very strict set of assumptions, and there's no way the problem can be solved within those assumptions. So for someone whose whole world is inside this paradigm, the problems appear to be literally insolvable, right? Insoluble, sorry. And here's a quote from Wolfgang Pauli, who's working sort of in this world of physics. He says, at the moment, physics is getting terribly confused. In any case, it's too difficult for me. And I wish I'd been a movie comedian or something of the sort and had never heard of physics, right? So you reach this sort of despair because the problems just can't be solved in that paradigm, and it's hard for those people doing normal science to think outside of the paradigm. But you will get a few, right, scientists who will look for solutions outside the paradigm. And here we have Heisenberg, right? So Heisenberg gets rid of the orbit, right, the system, and says something radical, right? Seemingly insane, really. Says, look, electrons just aren't in any particular position, right, until you observe them, and they'll collapse into a particular place. But otherwise, they're literally kind of in no place or many places at once, right? This is called superposition. This is like one of the fundamental crazy posits of quantum mechanics. So on the right, we have like Schrodinger's cat, right? So sort of a mechanism that sets up a situation where you got a cat in a box, you got a bottle of like poison gas there, a hammer set up, and it's hooked up to a little particle detector. And basically, what it shows is that if Heisenberg is right, and there's no real answer to like sort of the position of a particle until it's observed, if all this is happening in a box, um, there's no fact of the matter whether this cat is alive or dead until you open the box, and and all of a sudden the particle collapses into a determinate state. Then all of a sudden the cat will collapse into a determinate state. So some pretty wild sort of implications of this view, but um, this was the view, right? But it made sense of the data, and this is kind of a little empiricist sort of like move here, um, like I want what I care about is the observable, right? The empirical adequacy of my theory. I want to make sense of the observations, and if I have to posit some insane stuff at the unobservable level, then so be it. Um, and that's basically where Heisenberg went, and that's kind of I'm not deep into quantum mechanics, but as I understand, that's still the standard interpretation, right? Superposition is still a thing, um, and it's a tough pill to swallow, right? It should be if you're not sort of deep in this stuff and you've never heard of it and you're just first hearing of it. It should sound a little insane. So you can imagine if you were a physicist, been working your whole life under the assumption that every particle is always in a determinate place at some point in time, it's going to be maybe even impossible for you to swallow. And Einstein, for example, just never accepted what we call the new quantum theory. So that's kind of how scientific revolutions happen, according to Kuhn, right? Certain people that are used to one paradigm will just never give up that paradigm because the new one sounds too insane to them, right? And it takes sort of a whole generation of scientists to start to get used to thinking in the new paradigm before the theory is gradually accepted. And here we have a quote from the same fellow who was in despair, Pauli, a while back. Now all of a sudden he's very excited. He says, Heisenberg's type of mechanics has again given me hope and joy in life. To be sure, it does not supply the solution to the riddle, but I believe it is again possible to march forward. So here is one person at least who's excited about the new paradigm. And once you get a new paradigm, you have a new normal science, right? Different problems to solve, different rules about what counts as solving those problems, different assumptions. And this is then Kuhn's account of theory change, right? The first sort of inter-theoretic relation that we want to talk about. And just think, before Heisenberg, right, it never would have been considered acceptable to propose a solution to one of those problems, right, the Zeeman effect or whatever, um, by saying, oh, maybe objects aren't always in any particular place. Maybe sometimes they're in like no place in all places all at once. That would have been insane, right? People would have laughed you out. Now this is very standard, right? This is sort of what most everyone accepts when they're talking about quantum mechanics. So what does this mean, right? If Kuhn is right about this is how theory change works, first of all, it means that different paradigms are radically incommensurable, right? Which means they don't share any standards as far as like saying what's a good theory, what are the right kind of problems we need to work on, what counts as a solution to that problem. They just have very little in common that could help them sort of have any of the same standards, right, for what's a good theory. So this seems to imply that, right, the truth of a theory is totally relative, right? So how do we know who's right, right? If you have, particularly maybe before the change is total, maybe you have just the beginnings of the new paradigm, right? But it's not totally clear the old paradigm has run out of steam. By what standard could we say who is right? Because they can't agree on anything, any of the basic assumptions that you even start an argument about it. So this seems to imply that theory change is not a rational process. Instead, it's just sort of a natural process. What happens when the old scientists sort of die off, the new theory wins a few more converts, and it starts to sound more like political parties or like a religion or something than just like rational progression towards the truth, right? All of a sudden, it's a popularity contest, right? And this seems unacceptable to some people. In fact, we'll see that Lakatos does not like this account at all. And it's worse than that. It's not just the methods, right? Well, sort of what counts as a solution to a problem or what counts as a good theory. it's not just those things that are incommensurable. Kuhn also says that even if you're using the same term in, say, Newtonian mechanics and relativistic mechanics, like mass, right? That word appears in both theories. Kuhn says those words are going to have totally different meanings in the two paradigms, in the two theories. So, for example, when Newton talks about mass, he means something that does not change, right, as it speeds up. Einstein says, no, yeah, the faster you move, the heavier you get, right? And over here is the equation that determines how much heavier you get, right? Now, Kuhn argues that this is such a big difference that they can't even be talking about the thing at all, right? So someone in an old paradigm is speaking a completely different language than somebody in the new paradigm. Now, there's ways around this, right? If you're an empiricist, you might say, well, maybe the theoretical terms change, but observational terms, right? That'll be the same, and that's kind of what we care about more, right? Because again, for the logical empiricists, the theoretical terms are only good or meaningful insofar as they can be translated into some observational vocabulary. So if we agree on the observational vocabulary, then we can still communicate, right? So maybe there's a way out of that. Right? Kuhn seems to think it's a bigger deal than maybe the logical empiricists would think. But Kuhn is not even, he's not even going to go this far with the logical empiricists, because he says you can't actually make that clean distinction between theoretical and observational terms. He says observation is theory-laden. In a sense, what you see is determined by the paradigm you're in, by your background theory. And the quote is, though the world does not change with a change of paradigm, the scientist afterward works in a different world. What does that mean? I don't know. If you were to read the actual Kuhn, there's one thing people sort of get mad at him about is that he's a little poetic with his vocabulary. It's not always clear how well defined his terms are. I think Staley notes that he uses paradigm in like a dozen different senses, right? But just to sort of like on behalf of Kuhn, to try to make sense of what he's trying to say here, imagine that you are a budding physicist, maybe some of you are, right? And in order to look at a cloud chamber like we have here, right, and to see an electron, right, that takes a bit of training, right? The person off the street, if you showed them that picture, it would not occur to them that they're looking at an electron. They would think maybe they're looking at a hair on a piece of glass or something, right? So in order to see that, right, to make that sort of observation, you need a lot of training, and a lot of training in a particular paradigm, right, that makes certain assumptions that will then, after you're sort of indoctrinated into the paradigm, then you'll look at that and you'll see, an electron. I think that was the positron, actually, from Dirac's theory. So electron size, but veering towards the negative pole, indicating that it's positively charged. But at any rate, that's fair enough, right? If that's what Kuhn means, then sure, science is sort of so specialized and developed that in order to really observe things in the way that you're supposed to, that counts as a good observation in your particular discipline, you do sort of undergo a good deal of indoctrination to see what you're supposed to see. So to that extent, observation could be said to be theory-laden, and that could be a problem for a logical empiricist move out of this issue of the incommensurability of different paradigms. Okay, so if all that is the case, then is there even such a thing as scientific progress? Right? Because we don't seem to have any rational way to decide which theory is the best, because if you're in the paradigm of your theory, there's different rules for what counts as a good theory, which seems to imply that there's no rational sort of way to tell whether a new theory is any better than an old one, whether it's getting any closer to the truth. And Kuhn sort of bites this bullet a little bit. He says, but he says, you could say that the new theories are sort of more specialized. We use the word more articulated, right? We're sort of getting somehow a deeper grasp or more detailed grasp on the phenomena. but he sort of stops short of saying there's anything like progress. Um, and for us as philosophers of science, the last thing that Kuhn's account sort of should give us pause on is that, well, that's sort of our project, right? Is sort of using logic and rationally sort of critiquing or analyzing scientific progress to try to get to the bottom of like, how do we get scientific knowledge, right? What's the technique? What's the method? How is it justified? We want to understand all this stuff. Um, and Kuhn sort of pulls the rug out from under us and says, your tools, philosophers, are of no use here. It's not a rational thing. Um, but nonetheless, he does think it's useful in some way. So are we out of a job if Kuhn is right? Right? Should we shut up and let scientists sort of do their thing? I'll leave you with that little puzzle and see if you have any thoughts when we discuss this on Monday. But the next lecture for Monday will be on Lakatosh, who pushes back on Kuhn on several of these things and has his own account of scientific progress.